So welcome everyone. This is our first AI Institute seminar for the new term. And today we are very, very happy to have Mark, our very own Mark, to give to kick off the second year of the AI Institute seminars. So Mark, as many of you know, is an assistant professor here in the ECE department. Mark did his PhD at UBC. I believe you graduated at 2011. And then Mark did a postdoc at Oregon State University. And he has done a lot of terrific work in the AI field. Let me mention some of that. Oops, sorry. Sorry. Yeah. Okay, so Mark, of course, is a member of the AI Institute. He's also a research fellow at Element AI, which is a startup in Montreal. As I said, his research focuses on developing new algorithms in reinforcement learning, deep learning, manifold learning, and many other areas of AI. And today, Mark is going to tell you more about the AI Institute seminars, what we have planned for the coming weeks, for the coming months. And also, Mark is going to tell you more about the AI field, some of the very exciting research projects in his group as well. So let's welcome Mark.
Great. Thank you, Ellen. Can everybody hear me okay? People hear me in the back? Yeah? Okay. Great, thanks for being here. So we already gave you my background, where I came from. So if you have questions about these places, I'm always willing to talk about it. The other thing that I do with the Institute, along with Yao Ling, is I help run the seminar series. So when you can't get, if you're not organized enough to get seminar speakers for the first set, you do it yourself, right? So that starts off. But I do have lots of stuff to kind of tell you guys about. But what I'm going to do in my talk is actually integrate a little bit of like a review of the year in AI, although that turned out to be actually quite hard to do. So I'll give you something. Talk about what the Institute did, so some brief intro, and then I'll go into a couple projects from my own lab. So kind of more like popular press, what's been going on in AI. But then the bulk of the talk, I'll talk about kind of three almost case studies, like kind of different areas of research some of my students have been working on. And after I sent in the title and set it up, I realized I missed an opportunity to call this talk like a tale of ice and fire or something, rather than just AI. So I called it AI on fire because I have a couple projects on forest fires and actually combustion simulation, which seems fiery, but also, AI is hot. But also, I have a couple on snow cover in roads, so I missed that opportunity. But the three areas I'm going to talk about are these three projects on combustion modeling for like simulating, combustion engines in cars. We've done some work on helping to improve the models for that in a faster way. And actually, I'll be presenting that next week at ECML, the European Conference on Machine Learning. So this will be kind of my practice talk for that sub-portion. So definitely feedback on that part. Will be constructive feedback, will be very useful. And then talk about other projects that have come out kind of recently from students who have graduated or are continuing on these other kind of real-world applications, but that it led to challenging AI or machine learning tasks we had to figure out in order to get them working. And that kind of happens. And then I'll give you a little review. We'll talk about the upcoming seminars. I had the list there, but we'll finish on that. So just in case you've never been to our thing before, you're here just because you're interested, what's AI? AI stands for artificial intelligence, good. Last year on our first talk, Professor Jesus gave a really nice history of AI and all that, so I'm not going to do that. But everybody has their own definition. Your prof or whoever you talk to probably has their own definition. Mine is just, we're in AI because we're trying to use human brains or animal brains as inspiration for things that are possible for computing. If you believe that brains are computers, I do, most people do in here, in some way, then if some other entity can do it, our computers could do it. That's essentially the challenge, right? That doesn't mean we're trying to replace things that humans can always do. Sometimes it is really augmenting difficult tasks that people have trouble with and helping them make their decisions better, right? So I always say it's more about enabling human decision-making than kind of replacing people or animals, right? But it also helps us understand intelligence as well by trying to do that. So I don't have these rules down as kind of jokes, but it's not really a joke. But the definition of what's AI kind of changes over time. So what was AI in the 80s in the 90s, often now it's thought, well, that's just standard image processing. That's just face detection. That's easy now. And it used to be like this hard thing to do in the 90s. So AI is kind of thing that once you solve it and it's mastered, sometimes people don't think of it as AI anymore. So by definition, it's only bleeding edge. But it also means that the field keeps growing and old terms are still in AI, but new ones get exciting. So I mean, these days everyone's talking about, can you see my mouse? Yeah. Everyone's talking about machine learning and deep learning, and sometimes they call that AI, and all of AI is just deep learning, and that's not true by any stretch of the imagination. But there's also kind of older terms that people have used, which are really, a lot of research still may be happening in them, but a lot of the really easy or tricky fundamental questions have been solved. So we'll often talk about good old-fashioned AI, which is like everything before, I don't know, 85 or 92, which are like things that are pretty well understood, but there's still stuff to do there, like if the system's more complex, how do you control it? How do you define logical? Like many of these systems in the old-fashioned things were more that they were deterministic, or the systems were kind of well-defined. And now we often deal more with uncertainty or very large systems. So you could have a problem that was hard and now was solved, and now it's hard because you've got 10 billion data points, right? So another thing I always intro with is just kind of connecting. We used to talk about, people still talk about big data, the difference between big data and AI. They're completely different. Big data is about dealing with large amounts of data in some way. So getting into how to store it on your computer, how to access it, how to file it and run things in parallel on it. And often people want to use AI or machine learning on that big data, but they're essentially different tasks, right? They can be done separately. But a lot of machine learning and AI these days is dealing with large data sets and trying to get something useful out of them, right? So you can see this kind of pipeline of, you maybe have some big data tool, or maybe you don't, depending how big your data is. You have some way of storing your data. It's really, when it comes down to it, just tables, like spreadsheets of information. And then you've got to, in the end, the goal is, I think, always to make human decisions, right? That we're trying to enable people to do their job better, or not have to drive their car so much, or make better medical decisions. Usually it's aiming some real world kind of output. And then whether you're doing AI or machine learning is kind of a bit more about whether you're finding patterns in data and that's the full result, or whether you're using it to make decisions, or you're using it to generate language that people can find. It's kind of a gray line, right? They really are kind of parts of each other, and at different conferences, people argue about whether one's a subset of the other. It doesn't really matter, right? But everyone in this area is kind of working on the same things. We have complex systems. We know they're possible to do because animals and people do them. How do we get computers to do them, right? So that's kind of the intro of that. Oh, right, and then there's other buzzwords. So it's all about the buzzwords. I guess some of the ones I might mention that come up in my research are the red ones, but there's kind of a whole growing universe of them. And I think when I created this one, they're a little more like machine learning buzzwords to the left, AI buzzwords to the right, but they keep changing. And often people rediscover things that are older methods that are really the same thing again. So my particular research area, like I say, I'm trying to find ways to augment human decision-making, and with the most broad sense, whatever that could be, in complex domains, in dependable, transparent ways, right? So that means I have a lot of projects that are in completely different problems, but we use a couple underlying technologies to do that, right? So I talk about forest fire a lot because people find that interesting, but that's not actually my research about. It's just one of our great domains that we use. So I like to think of research, and maybe for grad students and people, not everyone thinks of it this way, but there's one way to think about your research career and the way to find new ideas and connect them is that, there's domains that have the data and have the kind of problems that you're looking for, the specific tasks that you're trying to solve, like at any moment, and then there's the methods you use for those, right? And they're really independent, but they're kind of, I meant to have arrows here, but you can go from any one to the other, right? You get a new idea because someone says, oh, I want to we've got this problem with combustion simulations, it's really expensive. They have this data and you figure, well, what are you trying to do? And then you find an algorithm that does it. So that's how I think of it. So in terms of my lab, some of the domains we work on are, like I said, forest fires and ecological problems where there's something spreading across space and time. So it could be a fire in a forest, or it could be an invasive species of bugs or plants, and you want to stop them or slow them down, right? So that's a decision-making problem, but it's also got a lot of prediction and other things. and it's complicated because the data is often hard to get and high dimensional. We've got a few people working on medical imaging. I'm not going to talk about that today. And then we've got a bunch of people doing driving control because it's Waterloo and is automated driving cars, so that's lots of people working on that. So some of the tasks that you would do, and when I talk about tasks, I mean these kind of like fundamentals of what is your machine learning problem, right? So classification, prediction, finding a good policy for making decisions, anomaly detection. Those are kind of the main ones I work on, and these problems cut across different domains. And then the different methods for trying to achieve those, I don't know if they line up. Well, they don't completely line up with the tasks because you could use multiple ones. But I do a lot of reinforcement learning. I teach a reinforcement learning course now in the spring, which we just had the first iteration of this past spring. And everything's deep learning, of course. But we also have some work in ensemble methods, like ensembles of like regression trees, and some theoretical work on data reduction, dimensionality reduction, manifold learning. Sounds like it's all over the place, but there is some unity. But the unity is really a couple different types of algorithmic methods, and the data kind of comes from many places. Yeah, so that's me. And then sort of in the role as AI seminar kind of host and kind of organizer, co-organizer, I was going to try to find like, oh, what happened in AI this past year? I'm like, oh, this would be easy. I'll look it up. I'll look on archive or like the conferences, and I can't even find like a common thread because there's so many publications and things happening. We try to look at NeurIPS or AAAI. So I need to improve that more to find them. But in terms of news, there were a couple big events, and that's probably good to just kind of talk about, the good and the bad, because they both lead to kind of interesting research problems. And then I'll dive in a bit more on my own research problems. So some of the positive things, which was good, is they had this, the Turing Award, which is like it's the Nobel Prize of computer science, right? It's the best thing you can get as a computer scientist or as an AI researcher, because you get your Nature paper, you get your Turing Prize. To get a Nobel Prize, you'd have to do something with economics or physics, right? So you could try to do it, but this is the big one. And so this year it went to, and so if you don't know who Turing is, you're not a computer scientist, but he invented a lot of the theory behind computer science. And he had many influences in kind of many areas of theory and computing. The most famous one, which you can see in a Hollywood movie, is about breaking codes and fighting in World War II, but it was also about algorithm complexity, the definition of what a computer is, and AI, because he would talk about the moment there was a computer definition, they're like, oh, how could it recreate human intelligence? So we talk about the Turing test, which is, if you could build a computer that fools a human, then you could call it intelligent. It's kind of the simplest, I think, worst definition of intelligence you could have, but it's something you can test, right? But this year, the Turing Award went to what they call the godfathers of deep learning, the founders of this research. So three professors, Jeff Hinton, Yasha Bengio, and Yann LeCun. A lot of Canadian connection because Jeff Hinton was at U of T and Yasha Bengio is in University of Montreal. Yann LeCun spent some time at U of T with Hinton. And amongst themselves, they did a lot of work through the 90s and even earlier without a lot of recognition and working on it, even though everybody's saying neural networks are dead. They kept moving it forward, and at some point in the early 2000s, everything started to fall together, and they started beating every other model in the world, and now everything's deep learning. And so they got the award for that contribution, and really each of them is given, contributed to different components of deep learning to get us to the place where we are. Hinton did a lot of fundamentals of the deep part, the fact that it's deep. He worked on those things. Everyone says it doesn't matter. It's still overfitting. Yasha Bengio did a lot of back-end things of getting them to work better, these adversarial, these functions, the ReLU functions that kind of cut off the really mechanics of getting the neural networks to train better and not overfit. And Yann LeCun kind of invented and spearheaded the convolutional neural networks, which are good on images. So everything you do with face recognition and these face shifter apps and stuff are all because of that. So that was a big thing earlier in the year that they got that award. Some other things, like I said, kind of things that are in the news. Another thing from every year you have to say, well, what did DeepMind do this year? They did Go a couple of years ago and kind of defeated humans at that. This year they were doing StarCraft, trying to do reinforcement learning and deep learning and even game theory to have automated playing of StarCraft. So this is kind of all the buzz earlier in the year. It also built a little controversy because they didn't release the code for it or the details of how to do it. They just said, here's the results, it works really well. And then they played a bunch of kind of human competitors in a very publicized thing, and it worked well. They mostly beat them. But people who know StarCraft, and I don't know StarCraft, were saying that it was kind of a simplified version of the game and a kind of more limited test. But as these things usually go, it's like, well, probably in a year or two, they'll beat everyone on every version of StarCraft. So that's where we are in terms of very large systems with unlimited computing power to kind of tack complex problems. I don't know the details of their model, but usually, as they did with the Go games, they have a lot of self-training. So one of the interesting things with this is that it's some of the trends that are currently going on. There's a lot of things on transfer learning and imitation learning. So using human demonstrations to bootstrap computer learning, and then after you've learned the model how the best human does it, you keep learning by playing against yourself, and then you keep kind of fine-tuning it. And they did that as well. And that's how Go solution worked at first. So that is a trend in the actual research, trying to find algorithms for leveraging expert knowledge to learn full models. And also just that deep reinforcement learning continues to grow. Another interesting kind of vector of these kind of things that are going on in research is this approach of doing more AI for environmental things or AI for social good. It's called AI for something good because there's like 10 different AI for a star good somethings. I was involved with this AI for social good workshop at NeurIPS last year, but there's a UN AI for good summit every year now, which is a couple days and brings in like politicians and social scientists and computer scientists and engineers to work on all that. And so it's really becoming part of almost every conference has some kind of workshop or track on this. So that's exciting. And the idea is that it's very vague, but it is really like any task that is not just making money, like advertising or stock prediction or something. It's like other problems like environmental, social problems, helping people find drug addiction therapy, like anything you can imagine, somebody's trying to do it, which is nice. Right, I said more details on the actual workshop I ran, but it's gone on. They've run it 3 times since last year's NeurIPS, and they'll do it again this year in Vancouver. And then I said there were some bad things, or at least some things that got in the press, kind of interesting and bad, and it's good to understand what they are. So one thing from a couple of years ago that was very exciting technically, and is still ongoing, is these generative adversarial networks, which is a type of neural network where you basically use input images, and you want to kind of output a new image that has a style of something else, right? So you can, the main idea of it is that there's multiple neural networks training, but they're adversaries. They're fighting against each other, and one is trying to generate predictions that are useful, and one is trying to criticize it and say that's not a very good copy or a prediction, right? And what it's been used for a lot is kind of training images on a set of images, training networks on a set of images of one type, and training it on kind of these transitions, and then generating new things. So you could train it on, lots of zebras and horses, or you could train on lots of zebras, lots of horses, and then you could turn the horse pictures into zebras just by saying, well, here's an input image of something, and I turn on the flag that said zebra and says I want it to be a zebra, and everything else filters out, and you get an image that looks pretty good, right, for a zebra. And people could use it. Initially, it's like, oh, this is going to be great. It lets you do, lighting effects, and like you can kind of modify images and make them more usable, and we could generate interesting data. And this year, we kind of got like the appification of it, that you could say, well, what you really do is you could just have this fun app where you make yourself look old, right? Because you have lots of pictures of people of different ages, and you can put your own picture in, and it converts your face to someone old. This is like a huge thing a few months ago. And you could do things where you make yourself look like a different person, but making people look like yourself when you're old seemed really attractive to people. In China, there was an app using a similar thing. This was made by some Russian company, and nobody knows who it is, and they have all the data of people who've used it, and they don't know what they're doing with it. So that was a viral thing that people were worried about. This was an app in China that let people kind of put their face on someone else's face, and that has all kinds of implications you could imagine, right, ethically. And that's starting to become this problem that, well, deep learning's great for this, but you could use it to fake things, and the whole fake news stuff is a risk, right? Because you can create things that are very realistic, but hard to distinguish from reality. And so that's an ongoing research task of like how to detect those and thwart them. So people have ways of trying to figure out how to undo that kind of detection, or how to detect that it's not real. The Cambridge Analytica stuff, which was more of a political thing, they were using the ability of like the fact that marketing and like your AI is good at selling you ads on Facebook and Google. They use the same technology to essentially do targeted political ads, right? And this is another example of like, it's a hard thing to stop from happening because it's another use of the tool, but it can have a negative social effect, right? So as researchers, we have to kind of be aware of these things and look at having ways to put in some kind of safeguards against them and awareness. And that happens at the AI conferences, but it's something to figure out technically how to do it. So in terms of the Institute itself, we had a lot of advances, and I got this slide from Chris, so I don't know exactly what's on it, but many researchers in the University of Waterloo, 18 projects funded with these. You get emails if you're in the Institute from different companies saying, we have this money, please submit a project proposal and we'll give you a project, so that's great. They have new academic relationships with different universities around the world, and co-ops. This AI for Social Good Fund I do know about because I got one of these Microsoft grants with Kate Larson in computer science. We're going to be able to do some forest fire kind of research on that. So there's a lot happening and a lot being pulled in, very industry focused, right? And then the seminars we had last year, and this will be the last thing before I get to my stuff. I'm worried I might have missed some because I kind of rushed at the end looking for all the old talks. So if I missed your talk, I apologize. I will add it. But we had some great talks the whole year round. Like I said, from Professor Jesus giving us a history of AI and medical imaging stuff. Vijay talked about sat solvers. Professor Cohen had stuff on security and multi-agent systems. We had game theory topic from Professor Zahidi. Professor Ben David gave a really interesting talk of like, here's what the limits of machine learning, and showed some kind of proofs and connections to that. So I missed yours. Yeah. Yuri's talk was in there. That's what I was finding on the website on models. And then in the new year, we had a few more talks on optical. I missed that one. Vasily's talk on optical emission spectroscopy. Kirsten's talk on human-robot interaction, and Professor Fantukis' talk on graph clustering. And like I said, there might be a couple others. At the end, we'll have the list of the upcoming talks as well, but it's going to be an interesting, wide-ranging year once again. So there's my review of everything that happened in a whirlwind. So to talk a bit about my research and how it fits into some of these trends, maybe, I had these 3 projects, right? And that's why I got my title of Fire, because a couple of them are fiery. So the first one is a very interesting project, and this is the one that's going to be, I'm going to be going to ECML to talk about next week. And we have one of the students who worked on it here. And the idea is in mechanical engineering and like in combustion engine and design, they build simulators, right? So you want to build a better engine that's very efficient and uses the energy well and the fuel consumption. You want to build a simulator of that, right? You can imagine fire dynamics pretty complex to simulate, right? They have the PDE equations that define every moment of it and how fire spreads and moves, but those are very complex to solve and run, right? So they have lots of different challenges in order to simulate, make these simulations. They had to handle turbulence. We're not looking at turbulence because that's a whole other ball of wax. But even just looking at the different levels, like the mixture of the fuel and the oxidizer, the air, and any other elements in there, how much heat gets released. There's lots of complex things, right? But they want to build a simulator of this. So we're just looking at the combustion energy itself, not turbulence. And so the prof, Jean-Pierre in mechanical engineering has this data and is an expert on that, and he was trying to find ways to say, well, can we make this faster, right? And so one model they use in that to do these simulations is a simplified version of flame. So rather than, here we've got the actual reality is that there's some fuel being shot out, there's a flame, and the energy reduces further on, and somewhere in here, the energy get used for your engine or whatever. Is an idealized version, right? But that's the reality. A simpler model, which is still quite useful, is this kind, where you say, well, let's take every point in the flame and say, let's model it by a laminar, what they call essentially a flat, piece of fire that is created by the pressure from the fuel coming out and the oxidizer, right? You got oxygen or air going in one direction, fuel in the other direction. You get this flat layer of fire, as I understand it. And you say, well, what's the temperature of that fire? What's the energy being released there? And you know things about what the fuel's made of, how much oxidizer is, what the pressure is between them. So you get a few variables, and you want to get the temperature out. Great. So you have a function, you look those up. Computing that is expensive. So if you want a simulator that's running very fast, it's not easy to do that. So what they do is they create a huge table with these 3 input variables, the pressure, progress, which is kind of a representation of the kind of the level or at what point in the flame you are, how far you in here, and the mixture, right? So they create this lookup table. Lookup tables already, for just those 3 dimensions, for the level of granularity you need for the simulator, it's like a couple gigs. And they run it in memory, and that makes their simulation run pretty well. But what if they wanted 4 dimensions, right? Because there's actually more to fire than these 3. There's like 5 or 8 they'd like. It's like, oh, then the table is going to explode, right? Obviously, if you wanted, every time you add 1 more dimension, the table is going to get exponentially bigger, right? So what do they have? They have 120 to the 6 entries just for the one they use. But for the one they want with like 5, it's 4 times 10 to the 12, right? It's like, this is not doable, right? You're going to need terabytes of data just to have your lookup. So the idea we talked about quite initially over lunch once was, well, why don't you use a deep neural network to replace that table, right? Because a neural network doesn't really care about how many inputs it has. If it learns the function, it can learn it. And then the output can be the temperature or pressure or whatever you want, right? And actually the initial reaction was, oh, people tried that and it didn't work very well. And so when did they try it? So like 2000 or 2010 actually, 2010, okay. And they tried it and it overfit, it didn't work very well. It's like, okay, well, some stuff has happened since 2010. Maybe we should try. And so we tried, and it worked pretty well. It's kind of, we had a straightforward kind of definition of this model. So the architecture is not revolutionary. What's interesting maybe that I'll talk about is all the tricks we had to do to get it to work well and like make it more productive, which is at least half of the work for deep learning. But this is our architecture for one version of that. So input, we've got those, we just still did the 3 variables because we want to compare at this point. It's just the first paper we have on it. Compare it to the existing tabular version. So we're just taking the original 3 variables we have, that they have a table that they look up. And then we have fully connected layers of neural network, increasing size and then flattening out. And this network is trying to predict the actual outputs, what proportion essentially of water, hydrogen, oxygen, and all the other things you have in the resulting mixture, right? So it's a simple prediction problem. You just want to get the numbers out there and you have an accuracy because you know what the actual output was. And they have experimental versions of this, or they can compute it exactly through kind of a few days of complex simulations. They can give us the actual numbers. So we get perfect, easy, supervised learning, training data, and we can use that. So for the other problems, we actually want to do prediction of temperature, this source term, which is hard to explain, and heat release. So essentially, we want to know how much energy is coming out, right? So we tried having one network to train all of these, but it turned out to not work as well as training separate networks for each task. And it's not that it couldn't, right? Because neural networks can learn any function you want, but as you often find, if you're trying to learn very different functions within the same network, you just need more data, right? And you might need a different structure or some clever architecture. So we might look at that later, but here we just said, well, we'll have a different network for each type of thing, the energy release, the temperature, and for these species. So along the way, we still found, okay, it had a various kind of weird problems. So one of the problems was it was oscillating. So the temperature seemed good often, but then it would just dip down and be like way off, and then come back up and be right. So we'd have this kind of oscillation stuff. And the student who was working on it, Sushwat, was like, you just troll the literature and say, well, there's this fix for that type of thing. We'll put that in. It's like, oh, this is overfitting, so there's a fix for that. And you just tried out different tricks that essentially helped compensate for each of these. And any deep learning paper you find usually has a lot of those. They might just mention it really quickly. In ours, we kind of took each one and did experimental studies of the effect of each one independently and kind of looked at them. So that was kind of nice. So the oscillating temperature is essentially, it's trying to overfit. So it's got some data points that are really well fit and other ones that might have been just lower, and it's trying to get like an exact curve that is hitting every point, right? And maybe we want something smoother because we know the reality is smoother. our data set is a bit noisy. We've only got some of the points. So why should we have something so overfitting, right? So the standard approach to that is regularization. You add some extra terms to your cost function for your neural network to say, well, don't have too many ups and downs in your output, right? And he tried different ones and found one where you're using L1 and L2 regularizers work the best. The classification error itself, so for classifying the levels of each output chemical, there was some problems, and he was using ensemble models for that, right? So an ensemble works in many models, right? We know them most famously from random forests. So you have one decision tree, and if you have, it'll fit one function a certain way. If you have 100 of them and then average the results, you can usually get a much better kind of error, better accuracy, right? So ensemble approach almost always improves what you're doing, rather than just saying, I'll have one model, I'll have 5, and average the results or take the best, because sometimes one model will do better than another, right? So that's not a complex fix, but it was helping a lot in our reduction. So we think he runs, like when you do cross-validation of the data on 5 different sets, essentially you had 5 different networks, and you'd run them all on all the cross-validated data, but they would all train on some subset of that. So we were trying to, and then we averaged the results for that. This one was kind of interesting, is that certain parts of the temperature curve, and I don't know if I have the temperature curve here. I don't. Yeah, this is kind of an example of the temperature curve. It's got, we're interested in parts where it's the hottest, but there's lots of really sharp other parts, so the slope changes really quickly, right? And so certain parts where we don't have as much data, like the curvature changes a lot at the high part. We don't have as many data points there. So it's more important to get that right than to get the exact slope of the drop here, right? Because we actually aren't using that as much. And so we found our data was kind of uniformly sampled from the simulator, which was our fault for doing it that way. But once we have that data, it's like, well, how do you utilize that when we know some part of the data is more important than others? So you can do oversampling or importance sampling, where you say certain parts of your data are more important to get right. And so we defined hard examples based on the error from the batch in general, and said we're going to oversample those, right? So it's going to affect our kind of ability to say it's learning to think from scratch, but we know that we're training more on the difficult examples. So we did oversampling, and that was kind of useful. Another thing was that there's a problem in deep learning that often happens is the ReLU function, so the activation function in a network. Go back to your neural network class if you've taken one. In the middle of every layer, right? We have an activation function, some non-linearity. So the ReLU function helps a lot with many problems that deep learning had originally, because if you think about it, we're following gradients, right? So the reason ReLU works better than sigmoid or other things is that at every point, you get a gradient for some data set, where you get some data points that say, okay, here's the true value. What did your network output? And you have a cost function that essentially tells you how far you are from the output that you're supposed to have predicted, right? And then you get this gradient that's either positive or negative once you kind of center it and normalize it. And so if the gradient goes up, you're learning a thing that's good, right? You're saying, okay, you're trying to recreate the positive cases, right? If the gradient's going down, it's saying you got something wrong, you should push your weights down and not do that thing you just did, right? And you think that makes sense. That's what people use for neural networks for years. They say, well, just scale it probabilistically, so that if you're really wrong, you push it down by more. If you're really right, you push it up by more. If you're close, you kind of don't move it by much, right? And what the people found experimentally is our ReLU, which says, if you're wrong, just ignore it. If you're right, push it up almost linearly. So the more right you are, push it up. But if you're 0, you're wrong, and your gradients are negative, just throw that out and move on, right? Don't worry about fixing your wrong cases, get the right ones right, because everything gets normalized anyways. So it seems to work better. But then some drawback is that we had all these zeros now, and you're losing a lot of data for no reason. So I guess the fix of this that people have been looking at is different types of ReLU. We used leaky ReLU, which doesn't get rid of the zeros completely, but weights them by some small number. So all those zeros are still in there. You're not just wasting those data points, but you're not fussing too much about the rate of them or curving it, and it helps with some of that training. So we found this to be pretty useful. So this one's showing, what are we showing here? Ablation studies. So a thing that's become quite common really only in the last year or two, I think, is ablation studies. And people in biology would be familiar with this, where you say, okay, I've got some, petri dish of this thing, and I'm going to test, or a mouse, I guess, and you've knocked out one gene, and you want to test another one, you need to have controls for all the things you're changing, right? If you change 3 things, you need to have versions of every one where you've changed just them independently, where you've changed nothing, where you've changed combinations. And machine learning people didn't do that until recently. We just said, well, I changed these things, and it's better. The accuracy is higher. And there's been a lot of problems with recreating results and being not sure where people are. So there's major push in research in machine learning, especially these days, to release code, but also release your methodology for experimentation, and to do these ablation studies. We say, well, we tried adding 3 of these things to regularize. Let's see how each one works independently and give the numbers, and then we give the full result of how they work together. So each of them independently seem to help with different aspects. The red line here is the truth that's computed theoretically. The bottom lines, so that we should have those all the same color, ideally, were the model that we'd proposed. And they're usually better, at least in some parts of the curve, than others, but they're not always superior, right? So then we have results, obviously, since we got published, that all of them together work better than the other methods. So the accuracy, it works pretty well. Comparison to this tabular method is kind of interesting because that's the thing people really use, right? So if we talk about serial here, so serial inference time is really the fair comparison where you use the table to look up the energy release for the flame, and then you put it in the simulator. And so obviously looking up a table is going to be faster than looking up a deep neural network because it's a hash table. It's like, look it up in memory. If you're smart about it, it should be quick, right? Querying neural networks is not particularly slow because you just run your weights through it once, but it's definitely slower than a table lookup, right? So we found, at least in the data we were doing, it was 5 times slower than the table lookup. But then for the neural network, it was also quite possible to parallelize the inference, so reuse some of the blocks of the samples and kind of, because we know in this case we were trying to compute all the values of the table, and so we could kind of like reuse the queries multiple times. So there's ways to speed it up quite a lot, so it was actually faster overall than the table. But that's stuff we're still kind of working on. But that's not really the point either. The point is that that's just for 3 dimensions. If you want to 5 dimensions, we don't have to change anything, right? You could have use the same kind of approach. You might want to make the network a bit bigger, but that you'd have to experiment with. But the idea that it has 3 inputs versus 5 inputs doesn't change. It should just work the way it works. And you use much less memory, right? Because the table is going to keep getting bigger and bigger versus the neural network. If it needs to get bigger, it's because it's reached some maximum capacity for that information. But this problem, in a way, isn't as complex as other things that people do with images. So it should be very possible. And then kind of the most, I guess, compelling ones is we ran it in like the actual simulator and regenerated some of these flames. And we did a couple of the steps being predicted by our network versus the table. And essentially, they came out very similar. But this is really just a first test of that proof of concept. What we really want to do is run it in full simulation where it only queries the network and then see how well it does, in simulating the dynamics. But that'll be next. So yeah, it was an exciting, very applied project. But then we got a bunch of different interesting tasks out of it in terms of learning how to set up neural networks for these kind of complex settings. So the student learned a lot how to do that. Okay, so I'll definitely talk fully about the second one. I might have to skip through the forest fire one a bit. So the second one is from a student who just graduated, Juan Carrillo, and he was doing this data project, and I kind of pasted these in at the end, so some of them might be formatted weirdly. The idea is to detect winter road conditions in Ontario. Essentially, the Ministry of Transportation has cameras around many of the roads, right? They have to plow the roads so that it's safe to drive. They always go out and plow the roads kind of quickly, and they do them in order of how important the road is. But it helps them to know how covered the road is when they're going out to decide if they should plow it or not, because somebody has to drive all their way out of the way to go there. So they have some cameras to do that, and they have other cameras that are not really meant for various cameras around the province that do different things. And so what we were trying to do here in collaboration with another lab on campus, that's where they got all the data set. We were just kind of doing another layer with it, is to help leverage the data that already exists and see how well you could do at classification and prediction of where you're going to need to plow next, right? And I guess this one Yeah, so they have a labeled data set they created in this other lab in urban planning, where there's essentially 3 layers of road. So there's clear, partially covered, and fully covered road. And so you have to plow the fully covered ones, right? So yeah, around Ontario, there's these different sensors. So there's the road weather system, which has cameras and weather monitors and everything all built in, right? But they're not on every road distributed across all the highways, right? There's some very detailed sensors that are just cameras that are used for traffic that Ministry of Transportation runs. They don't have weather sensors connected to them, but they have visual cameras so you can see some images, right? And then these Environmental Canada weather sensors in different locations that give you weather but don't have cameras. So we've got a bunch of things like sensors. We have a ground truth of sensors that have everything, and we have other ones that only have some part, right? And so the result was we had this map of Southern Ontario, and each color is one of these different types of stations. You know, obviously, the 401 has more of the cameras for traffic. The weather ones are distributed kind of evenly, and there's others. And so Juan was looking at ways to use machine learning to help use all this data to make better predictions, create a prediction map across the province, right? I won't go too much detail into it, but the idea was part of it is you have to predict weather, right? So the probability of there being snow on it is like related to it if it's cloudy, if it's snowing, so you want the weather predictions for each area. But sometimes you have a camera at a place where there's no weather station, right? So what he did was looking at the nearest cameras kind of nearby, using like nearest neighbor kind of clustering, and then did interpolation of the expected weather conditions at the location where you had one of these cameras that has a camera but no weather sensor. It's like, well, what's a combination of the road view plus the weather? And conversely, in the places where you have weather but no camera, you want to use the probabilities you have from the places where you've seen road conditions, and you do classification on those images and say, well, how likely is it that those roads are covered, given that we know it's snowing here, but we don't see the road. And so we did a bunch of things on that. What did he find? Well, I think this one I got a little out of order. Let's see if I have his network. Right, so he did a bunch of different studies trying to show how different network structures worked. And he had a funny situation where there was a big deep learning model that everyone uses. I don't remember which one it was. It might have been Inception or something. So something that's quite deep, really heavy, and lots of parameters. And people had tried to use that to do it for this problem, and it got some fairly good results. And he was trying to find ways to improve that. So let's try more layers. Let's reduce the size of the layers and see the different components. And he's trying to do the same kind of ablation studies I was talking about before, and saying like, well, I need something to compare them to, right? So I'll create a simple, like a dumb version of the neural network, which is like 5 layers deep, fully connected, and see how well that works, right? It'll be his baseline, he called it, right? And then you run the baseline, and it worked really well, like better than the huge network, right? Because the problem wasn't in some ways that complex, or the other one was overfitting, and really, or it didn't have enough data to train it because it had so many parameters. And there's an interesting data set here, but it's not huge, right? And so a smaller network was easier to train to a level where it had high accuracy. And that was one of the things he found. I don't have the slide of that network. So what else did we say here for the conclusions? So we got 2 conclusion slides. Yeah, so I guess we found that adding the weather stations in increased from the previous accuracy that he had, which makes sense because you have more data. And the simpler model beat out the kind of heavyweight ones. And yeah, and then there was also still, and even in that approach, there was a trade-off between using a simpler model with like kind of SVMs and radial basis methods for predicting it. That was much faster, but the accuracy was kind of a fair bit less, but it depends on what would be needed, right? So if you're trying to deploy this, you might still revert to a simpler model. But it was one of those cases where a simpler network actually was better. So a little time to talk about the third project I want to talk about, and this one I've talked in other talks before, but it's forest fire. And so this one I've been doing forestry, forest management and forest fire since my PhD time. That was my PhD on kind of planning and like harvesting in forests in a sustainable way. So there's been a history of doing this, and then recently we're still kind of, one of my PhD students is working on it. The main idea is there's forest fires. They're a big problem, especially in Canada, but even recently in other parts of the world, right? I wanted to update this one, but there's the big fires in the Amazon this year. There's huge grass fires in Australia right now. And so everyone knows there's a big problem, and there's lots of tools to deal with it already. There's experts in these fields who run complex simulations and optimizations to help them decide what to do in every situation. But there's a bunch of things that are changing. The fires seem to be getting bigger, right? A lot of that's climate change, that it's warmer and drier in the regions where there are the forests. Some of it is human management, that the past history of the way that forests, especially in Canada and the US, have been managed is that they were kind of planted very uniform so that they could be harvested easily for wood. And that means when they burn down, they all burn down, right? Now they're all old because they were all planted 100 years ago. Old trees are more flammable. And also the approach of putting out fires. So putting out fires because people live in a town, hidden, deep in the forest, means that the dead wood and brush and stuff on the ground doesn't go away, right? And contrast to what some presidents say, raking it won't help remove it from the forest. The most way that they usually get rid of the dead wood on the ground in the forest is to burn it and do like controlled fires and then let it go out, but make sure the fire doesn't get into the tree itself. Because many of these trees can survive a little bit of fire. They actually need it for their seeds to open. So we kind of stop that by making sure that all fires get put out within a day or two. And now the fires are so big, we can't put them out, right? So all that being said, the situation's changing dynamically. The models people have been using in forestry can't keep up necessarily, and they're being asked to do harder things, which is to protect everyone and stop the fires simultaneously. And the situation that their models were built for is changing because the climate is changing, the dynamics has changed. So the idea is there ways to use machine learning, AI, to leverage data directly to learn these models to help us make those decisions better, just to augment the decision-making that people are doing right now, right? The AI is never going to tell you to go out to this section of the forest and drop water here or cut that particular tree, but it's going to say, this area really isn't more risk given everything we've analyzed. Here's the strategic trade-off you need to consider, right? And they're already overwhelmed with so much data. It's one of those things, just like in medicine, AI is helping a lot because there's lots that can be automated, but the people that are making decisions are so overwhelmed. Even once we reduce their cognitive load with these tools, they'll still be completely busy all the time, right? It's similar in some of these environmental domains. I guess some of the things then that I work on, recently been getting more into like fire suppression models, but historically I did things with harvests, so like it's very spatial and complex, how you decide where to cut or grow new trees. And how do you model fire spread itself? So we did a project, which that's what I can show you a bit of, using reinforcement learning on satellite data, where we treat it as an agent-based model, essentially. And a lot of people in forestry use agent-based models to build a set of rules that describe how fire spreads. Again, often it's a very complex model and slow to run. And we were trying to learn that directly from satellite images. So we had satellite images of fire locations and smoke and spread. And then we'd have an agent, essentially the agent is the fire, deciding where to walk next, right? Do I go this way when I burn or this way? And the way the agent moves is depending on the wind, the dynamics, whether or not that area is flammable and like dried wood or not. And so we applied reinforcement learning, which is kind of a different way of using reinforcement learning because we weren't trying to make decisions, we were trying to predict spread. And we had some good results. So we had a few different papers on that over the last couple of years, trying to show how we could learn agent-based models from these satellite images and compare them to kind of more supervised methods. And at least in the area we were doing, comparing to Gaussian processes and some other ones, it seemed to work better and learn kind of more holistic models that model the fire better. But one of the problems with this is that the data is always often very noisy and kind of low resolution. So we're trying to get higher resolution data and as well use simulations. So we're building a simulator for forest fire that's kind of accessible and usable for current machine learning approaches. And then we're going to use that to do the kind of deep learning training that we talked about with StarCraft and other things, saying, well, if you can learn on this game and maybe people can guide it, then you can apply it to real world problems. So you give it essentially a leg up so it's not starting from scratch from these images. Because that's another trend that's kind of people are talking about more in machine learning recently, is that there's been a focus in research on end-to-end learning, that you have to go straight from the data where your model knows nothing and then learn it. And recently it's been more like, well, you have expert data, you know how to drive the car, why should you learn to drive it from scratch, right? You want to be safe, you should put in the rules that you know and then learn from there. So that fits with this. And this problem has a lot of other policy implications and connects a bit with that AI for good stuff, is that we're trying to build tools that different communities could use to make their case about what's important for fires or for ecology problems. So it's kind of an interesting area to look at, because there's not just one client or one user. There's many people who would find this useful, and they have different value functions. They have different things they want. So AI has the tools to be able to do that, but it's not completely clear how to do it. It's not something that you can get off the shelf, right? So there's definitely research questions there. Yeah, so that's my the topics from my research. And the most important part of that is that a lot of the work, most of the work, as we all know, is done by the students. So that's my lab. And the 3 topics I was talking about were those students. I guess most importantly right now is Juan's looking for a job. So if anyone needs someone who does that and knows GIS and did the snow covered project, he's around. And then, yeah, I guess the 3 highlights from this, and I'll just leave the seminar series up as well, was that for the combustion project, that sometimes a simpler model actually can work better, because you might have enough dimensions you can capture it with something simpler. And you should always check. So you should always compare to simpler models. Don't just compare the latest 3 best models out there, the most complex ones. Go back and try logistic regression. Try a simple network or SVM. And for the snow cover problem, we were finding that as well. So that was the snow cover problem. The combustion problem, there's standard methods that people use to make things fast, like table lookups. You can often do that with networks. And then the RL one for fire is that you can use some of the methods you have in creative ways. Like reinforcement learning is not exactly meant for what we were doing, but sometimes it works, right? Yeah, and then I'll just leave up the seminar series for the upcoming year. It's very exciting. So far, I think we have one almost for every month. I don't think we've figured out February yet. But next month, Pascal Poupard from computer science is going to come and talk about deep reinforcement learning. And then we're going to have stuff on the neuromorphic computing from Chris Elias-Smith. We have a visiting prof from UT Austin in December, just as people are on their way to NeurIPS in Vancouver. Some of them are stopping by and doing this, so that's going to be great. In January, Roger left, but he's going to talk about quantum computers, and he has always really great talks, so you should make sure to come to that. Kate Larson from computer science is going to give a talk in March on yet to be decided. Always great talks from her. And then new arriving prof, Katja Mumbar, who's going to be joint with system design and mecha engineering and has a big CRAC position, does human-centered robots, so she's going to do kind of later in the spring. So that's everything. If anyone has questions, please feel free to ask me. Thank you.
Is there questions for Mark?
Everything made perfect sense. That's good.
I have one.
Good.
So for the fire project,
Yeah.
we know we have firefighters, right?
Yeah.
And they are out there, and they're monitoring the fire in real time. Like, is there any way to incorporate the human part into the system so that we can give them guidance, in real time?
Oh, right. Yeah, I mean, yeah, getting real-time guidance to people on the ground would be, I think, a future kind of goal of these things. Right now, when you talk to people in forestry, they seem to be more interested in, because the way it often works is in the morning, very early in the morning, there's a strategic meeting at the main office in that part of the forest, and the managers look at the map, they get all the sensors and drone info from that night or that morning, and they decide what to do, right? And they send out teams of people there, they call in a water bomber or whatever. So you want to help during that meeting, helping them analyze, and then once the day goes, everyone's just out doing it. So it's kind of more strategic planning at this point, and they don't seem to necessarily want a computer telling them at every moment what to do. But you could imagine collecting the data and be like, well, I just noticed this, that doesn't fit what we said. That would be great to give feedback, at least for next day's planning, right? But yeah, that'd be great.
But then how do we account? Like if the algorithm makes a mistake, like how do we, like the accountability issues here?
This
how do
is
we
a
deal
big
with
problem.
that?
Yeah, so I mean, many areas, especially again, medical people have this problem too, right? You can give the AI, it's going to give you advice, but who's responsible, right? Your job, your career is on the line. You're the person who made the decision. So you need to basically, it needs to be a decision aid, and you need to provide, confidence bounds and even explanation of like, where did this reasoning come from? If you can build a causal chain that tells you why you're giving this advice, then that person can justify what they're doing. Because if they just say, well, the AI told me to do it, that's not going to be good enough. They'll get fired, and we'll blame the AI, so it's bad for everybody. But it really is, it's helping them make decisions. That's why I always frame it that way, because there's actually resistance. They don't want to use it. They'll say like, oh no, we got our tools. Like, you can't, I was at a workshop on this once, and we talked about, once you start talking about neural networks, like, well, it's a black box, and then we talk about black box nonstop. Like, the fact that they can't see what the weights mean was a big deal, and people are trying to switch that around these days and say, well, it's not, you don't ask what the neurons in your brain do individually, right? But you talk about areas of your brain. They do vision, they do language, right? But you never ask what each neuron does, right? And neural networks are much simpler than that, but that's probably the right way to think about it, that we could analyze why it's giving advice, but it's not that it's a black box of the weights, right? But that needs to be solved, right? To give a better explanation of the advice, yeah. Other question? Yeah,
Yeah.
go ahead.
Just a very quick question.
Yeah.
So you mentioned in the beginning medical problems, medical image analysis. Do you still work on those, or?
Yeah. So I have a student, Laura Kraken, who's doing medical imaging with diffusion MRI images. I'm trying to do classification of Alzheimer's disease. And then I have a new project kind of with Professor Tejus, it's his project, and there's several of us on it, for digital pathology, which is they take samples of tissue from people, and they look at it in their microscope, and then they want to figure out what disease you have or not. And the thing is doing search, trying to find related medical records for similar. So there's image classification and then search in NLP documents. So that's kind of just starting. Yeah, it's not my main focus, but it's a big topic. So yeah. Any other questions? Yeah, let me get you the mic so they can get it on the camera.
Hi, so this is a question from someone who doesn't know anything about this. So it seems to me that once you have something that you want to solve with deep learning or something like that, and you need to build a network and all that, you're kind of guessing what kind of network to build. And then once you make it, you notice, oh, there's a problem, the temperature dips. Then I fix that, then I have an overfitting problem. So it's always kind of like fixing problems. So is it always some kind of, so if you read a paper, you see how someone else solved it, and then you try that, and it's always some kind of inspiration in the moment. So there's no like kind of unified theory of which neural network to use for which problem. Is that
No,
true?
That's true. Yeah, I think it's maybe, hopefully we can get there someday, but it's still in this phase where it's kind of exploding and people try out a new thing, and there is a bit of motivation in the field in terms of publications just to always invent something new and have a new acronym for your algorithm. But sometimes people do reinvent things. But it feels like, yeah, we're still in the Wild West phase where people try out new things and you figure out which ones work. And it will stabilize, hopefully, eventually to say, well, these are the best way. I mean, CNNs, we know they're good for images, so there are some things that people know, but it's still quite open-ended, yeah.
Okay.
Yeah.
And also, it seems that you mentioned at some point, oh, if I do it like this, then it's better.
Right.
And that goes into a paper or something.
Oh, yeah.
But is it quantified?
It is, yes. I didn't want to go too much detail on this, but yeah, I mean, we're quantifying it by, and I think in this case it was mostly about the accuracy, like of how well we classified it, because we have a perfect model to compare to. But you could look at kind of the rock curves and the precision and the variance of it. So yeah, it has to be quantified as well. But there is a little bit of that in machine learning these days, of that as long as it's got higher accuracy, it gets published, right? That people are pushing back against that, saying, well, is it a better model? Is it faster? Is it clearer or simpler or something? Not just slightly more accurate.
Yeah.
So there's kind of movement to kind of get it more like the other sciences that do this already. But it's a bit of it's an effort to do it.
So you'd say that there's people who are trying to work on, more of a theory of what are
Yeah,
these
and
networks?
reproducible. I mean, in terms of experimentally, there's like a movement to try and do more reproducibility to make sure at least everyone can rerun your experiment exactly and get the same result, because they're finding, well, if somebody had these great results, and then if you run it again with different random seeds, you might get actually quite different answers. It's like, oh, you have to randomize over the seeds you were running on, right? So it becomes hard to figure it out. But there isn't an underlying theory, like neural networks work because they're a hugely over-parameterized function that can fit any data. So that's why they work, but what's the right structure for each problem? There isn't a theory that tells you which. You just have to read papers and see, well, people find this, at least for now. Yeah.
Thank you.
Great.
Yes. Okay.
Hi, Professor. Thanks for your talk.
Yeah.
I'm curious about your forest fire RLL project. I'm working
Yeah.
on simulation of biohazards and pollution, so I hadn't thought about doing RL for it.
Mhm.
I'm just curious, so your agent is the fire, and then the reward signal is
In
whether
that-
or not it spreads to, it gets the reward if it predicts where it spreads next?
Yeah, because in that case we
Okay.
had satellite images that we could see what happened next.
Yeah.
So essentially it was accuracy. Did you predict it
Right.
correctly, right?
But how do you know that the place that the fires spread was the optimal place for
Yeah,
it
it wasn't trying to
spread?
optimize it to say this is the best way. It was more
Okay.
we're trying to learn a function that represents what actually was happening of the fire dynamics.
Right.
And it worked well in that simple problem, but kind of as we've made it more complex, we realized it has to have a bit of other aspects to it.
Okay.
But yeah, it was basically trying to learn the underlying function of that dynamics.
And how does it generalize to fires it hadn't seen before?
Yeah, we had we had other fires in the same region.
Yeah.
So we had other fires in Alberta that we tested it on, and we trained on one on Fort McMurray fire and tested on other ones, but it might work quite differently in a different region with different climate or altitudes. So
Okay.
we didn't test that yet.
Okay.
Yeah,
I'll keep my eyes peeled then.
Yeah.
Thanks.
thanks.
Any other question? Okay.
What was the time scale for the fire prediction? Would it predict the next day or the next 12 hours? And how did you gather data for that?
Yeah, that's the thing we've been trying to improve, because we had some older satellites. It wasn't even MODIS. It was Landsat. So the images are several days apart. And then we were doing predictions by the minute, but then we would run it until we get to when the next image was, and that would be the prediction. So I don't know if it was minute or hour, but the model is making predictions over many steps until it gets to that one. But the idea we want to get, we're trying to get some more MODIS data now. That's every day you get an image, and so you can make a prediction that's really one day at a time. That would be better. Yeah.
Okay, so if there's no more questions, let's thank Mark again.
Thank you.